Vibration analysis. Time and frequency analysis technique. Multiple frequencies. Comparison between linear and nonlinear systems. Some comparisons between a high-frequency writing, a low-frequency, and amplitude modulation are: number 1 is, the envelopes at the top and bottom of the signal are in phase for a high-frequency writing, a low-frequency. The envelopes are out of phase for amplitude modulation. Number 2 is, for a high-frequency writing, a low-frequency, the zero-to-peak amplitude of the envelope is equal to the amplitude of the low-frequency. For amplitude modulation, the zero-to-peak amplitude of the envelope is also equal to the amplitude of the low frequency. The zero-to-peak amplitude of the highest peak is equal to f1 added by f2, and the zero-to-peak amplitude of the lowest peak is equal to f1 minus by f2 for both a high-frequency writing, a low-frequency, and amplitude modulation. Number 3 is, in rotating machinery, a high-frequency writing, a low-frequency, there is no cause-and-effect relationship. There are two independent frequencies and two independent problems. In amplitude modulation, there is a cause and effect relationship because there are two or more frequencies and only one problem. Number 4 is, when a high frequency rides a low frequency, the reciprocal of the envelope time period is equal to the low frequency. In amplitude modulation, the reciprocal of the envelope time period equals the difference between frequency 1 and frequency 2, or f1 minus by f2. When two frequencies beat together, such as in figure 27, there is a cause and effect relationship. Therefore, two frequencies are present, but only one problem exists. The 29.6 Hz frequency is the carrier frequency and is the effect of the problem, that's the motor is loose. The 25.6 Hz is the modulation frequency or modulator and is the speed of the fan driven by the motor. The only way the fan can shake the motor, in this case, is when the motor is loose. Looseness in the motor allows the motor to shake, and the two frequencies to beat. Amplitude modulation also occurs when two frequencies are not exact multiples. Figure 28 contains two frequencies with second harmonics. The two frequencies are almost the same, but not exact. The signal seems to be constant. However, figure 29 contains the same signal with a longer time period, and it is clear the signal is changing. Figure 30 contains a full beat and amplitude modulation is evident. The difference between frequency 1 and frequency 2 is 0.2 Hz. Therefore, one beat takes 5 seconds to complete. As the frequencies get closer together, the time to complete one beat becomes longer. Therefore, it is extremely important to determine whether the frequency is a harmonic or is just close to the harmonic frequency. The beat in figure 30 is a common signal from a 3600 RPM motor that has an electrical problem. The motor speed is 60 Hz minus the slip frequency, when under a load. Line frequency is 60 Hz. In this case, the motor speed and line frequency must be examined with enough resolution to identify the true problem. Thank you.